Hey everyone, I'm asmollizard, and today you get to delve into my mind as I try to solve this vectors question from RV's 2019 paper. So do give it a shot and I'll see you guys in about 3 seconds. Alright, so here's how I do it. So we have given two equations of a plane and we want to explain why they intersect. Alright, so first part of I, so you just need to examine the relationship between two planes, which are parallel, if not intersect. So if they're not parallel, they definitely intersect. So that's what we need to prove. And how do you prove that two planes are not parallel? We use the idea of a plane, right? Which is mainly the normal vector to the plane. All right, most of the things you do in vectors regarding planes would always involve the normal vector. All right, of course there'll be rare cases where you get the normal equation of or vector equation, which is r equals to a plus lambda b plus mu c, but mostly that equation is not really used. All right. So how do you prove that they are parallel? Well, very simple. Look at their normals. 154 is not parallel to 1 minus 1, 1. Therefore, plane 1 is not parallel to plane 2. As such, plane 1 intersects plane 2. Right, as simple as that. Next part, determine the Cartesian equation, is very similar to finding the intersection point between two graphs. You either sub one into the other or you solve a simultaneous equation. So put these two equations in a simultaneous equation. Don't forget to use the negative sign and not the minus sign. Then click on solve. You'll get x equals to 4 minus 3 over 2t. You can use lambda or whatever for the parameter. You then have y equals to minus half t, and then z equals to t. From here, you just need to, Cartesian equation. So take note of that. Either make t the subject or you find the line first, then convert to Cartesian equation. And since I want to use the line again in part 2, I think I would change it to the vector form first. So from here, 4, 0, 0, plus t. Now 3, 1, minus 2. How do I get 3, 1, minus 2 from minus 3 over 2 minus half t? I simply multiply it by minus 2 because it doesn't matter. This is a direction vector, not a specific vector. So they're still parallel at the end, and you can actually do that. Alright, so don't forget, t is part of the real number. From here, get the Cartesian equation, basically making t the subject. Just imagine x, y, z are here, then making t the subject for each x, y, and z. Alright, so I have zx minus this 4 first, then divide by 3 equals to, well, y equals to t, so z equals to minus 2t, so z over minus 2, or minus z over 2, both will work. Alright, so that is the line L. Next part, plane 3 contains line L, and we want to find, plane 3 contains the line L and has the point Q 5, 3, minus 6. Find the Cartesian equation of P3. Okay, so how do you find the Cartesian equation of P3, or a plane in general? We will need the normal vector. But we're not given the normal vector here, which means we need to find the normal vector. And how do you find the normal vector? Two direction vectors of the plane, cross them, get the normal vector. Alright, so we need to find two direction vectors for the P3. We have one already, which is line L, which is 3, 1, minus 2, or whatever that you found just now, right? Could be minus 3 over 2 minus half 1, right? It still works, don't worry about it. Then what's the next? How do you find the next one? That's the reason why they give us point Q, for us to find a second direction vector, which means that we need to find another point in the plane, and I will use the point from line L. I will be using 4, 0, 0 because that's what we have found. Alright, so I'll take 5, 3 minus 6 minus 4. Alright, let me just write that properly. 5, 3 minus 6 minus 4, 0, 0 equals to 1, 3 minus 6. Then from here, I will start crossing the vectors. 3, 1 minus 2 cross 1, 3 minus 6. Okay, how do you cross vectors fast? Very simple. First element, cover the first row. You cover 3 and cover 1. then the remaining numbers down and then up. So down 1 times minus 6, up minus 2 times 3. Alright, don't forget, the first one is always plus, the next up would be minus. So down is plus 1 times minus 6 is minus 6, up is minus 2 times 3. So minus 6 times minus 6, or rather minus 6 minus 6, which will give us 0, because it's just simply minus 6 plus 6. Alright, now second row, cover the second row, this time round up and then down. So up is plus, down is minus. Basically the first action is up, second action is down. Oh sorry, first action is up, first action is up, first action is plus, second action is minus. First action is plus, so minus 2, second action is minus, so minus 18 is simply plus 18. I have 16. Alright, last row, back to normal, down and then up again. Down is plus, up is minus because the first action is down, second action is up. So down is plus 3 times 3, which is 9, then minus 1 times 1, which is minus 1. So 9 minus 1 is simply 8. I can factorize 8 out to give us 0 to 1, and then I find the normal vector 0 to 1. So simply find the equation of Cartesian equation of P3, r dot 0 to 1 equals to, for take any point, because r dot n equals to a dot n, so this simply equals to 0. Alright, so we have the Cartesian equation P3 as r dot 0 to 1 equals to 0. Alright, so describe the geometrical relationship between these three planes and L. Very simply, if L is inside plane 1, plane 2, and plane 3, I think it's quite simple. All three planes intersect at L. Alright, so it's sort of a difference compared to some other possible relationship. Either they don't intersect at any particular point, or they intersect at a particular point, or they intersect at L. Alright, so these are the few possibilities that could arise. So that is part 2. Alright, so now we move on to part 3. Okay, so part 3, which is the line M passes through the points S and T. Find the position vector of the foot of perpendicular of S on P2. Alright, so we want to find the line M, right? Because, well, we're gonna seem to need that. Alright, so find the line M. So line M equals, or rather line M is R equals to, now we have 1.400. Okay, it's actually a point on line L, so let's keep that in mind. We might need to use it, or we might not need to use it. Okay, so that's that. So 400, which also lies on L, as I mentioned just now. Now to find the direction vector, well, just take one minus the other. So we then have 400 plus lambda 4 minus 2. Okay, let me just write that properly. 4 minus 2, 0, where lambda is any real number. Then you want to find the position vector of the foot of perpendicular of S on P2. Alright, so once again, dealing with planes, use the normal vector. So if this line M passes through 4, 0, 0, and what we notice is that 4, 0, 0 lies on P2. That makes our life easier because, well, we also know that 4, 0 lies on L. Alright, so, and P2 has L, so we can just use that point 4, 0, 0. Okay, foot of perpendicular on the plane 2. So if this is plane 2, the foot of perpendicular is here. And this vector we know is the normal vector 1, minus 1, 1. Now, some of you might ask, why can't it be minus 1, 1, minus 1? It can possibly be minus 1, 1, minus 1. But if we were to use the method I'm going to use, it doesn't matter at all. Alright, and the method I'm going to use is projection vector. Why? Well, because we know that this is S, right? Perpendicular of S on plane 2. S we know it's 0, 2, 0. We have a right angle triangle. So, and I want this particular vector here, which is basically me shining the light from here. If I shine the light from here on T to S, basically this line down here, my shadow would be this one here. And I have the normal vector, the direction vector, 1, minus 1. Alright, so that is the whole idea of me using the projection vector of TS onto the normal to the plane. Okay, so right angle triangle is very useful when it comes to planes because it allows you to use projection vector, length of projection, and sometimes even the Pythagoras theorem. Of course, there are many other ways to do it, such as letting the foot of perpendicular to be P, then taking the equation PS and then dotting PS dot PT and then find the value. Alright, but I find that to be a bit tedious for my liking, so I'll stick to the projection vector. Okay, so a very simple projection vector formula. First, we find the direction vector of TS or ST. Since I want this going downwards, I want to go from S to this point here. Let's say this is actually point P. I want to get SP, which is pointing downwards. That means I want to find ST, which is pointing outwards as well. Alright, so ST is simply 0, 2, 0, or rather it's 4, 0, 0 minus 0, 2, 0, which we found earlier. 4 minus 2, 0. Right, when we were finding the direction vector of the line. Exact vector, now I dot the normal vector. Remember, projection vector has no modulus. Divide by the square of the second vector, the normal vector. Share the modulus of the normal vector rather, so which is 1 square plus 1 square plus 1 square, so that's 3. Then dot, or rather multiply by the second vector, 1 minus 1. Alright, so this is basically A dot B over mod B square, and then B. Alright, so this is a projection vector formula. So from here we just need to solve. Again, quite simple. 4 times 1 is 4, minus 2 times minus 2, 1 is 2, so 4 plus 2 is 6, 0 plus times 1 is simply 0. So I get 2, 1 minus 1, 1, which is simply 2 minus 2, 2. Alright, so that's the vector SP. So to find the foot of perpendicular is simply 2 minus 2 plus, well, projection vector from the point S. So it's 0, 2, 0. And that will give us the position vector of the foot of perpendicular of S on P2. So it's simply 2, 0, 2. Alright, so that is it for finding the foot of perpendicular. Now, hence find the vector equation of the line of reflection of M into P2. Either you use midpoint theorem or a very simple idea, because the point of reflection is simply, well, this point here, and it's basically the same vector going from P to the point down here, right? So let's say this is S prime. P to S prime is simply the same vector as SP. Alright, so this is just a mental note for you guys. SP, vector SP is same as PS prime. So very simple. Vector PS prime is simply 2, 0, 2 plus the vector SP, which is found it to be 2 minus 2, 2 equals to 4 minus 2, 4. Then we know that that's the position vector on the new line of reflection. The direction vector, well, 4 minus 2, 4. We know that T is still on the point in the new line. So finding the new direction vector minus by point T, which is 4, 0, 0, simply equals to 0 minus 2, 4 equals to 2, 0 minus 1, 2. Alright. So equation of the line M. So let's can leave it as M prime. R equals to a point on the line, 4 minus 2, 4. You can't factorize this out because it is an exact point. Plus, let's say I use lambda, I use T, so I'm going to use mu, 0 minus 1, 2, where mu is a real number. Alright, so that is that for this question, and I'll catch you guys later.